Hello, and welcome to Edexcel demola. And today's lesson we are covering alkanes. We're going through properties, reactivity, the whole lot. No time to waste because there's a lot to cover. Let's get into it. Okay, so we're going to kick things off by talking about the property of alkanes. Now, we've covered general formula before. For alkanes, it's CnH2n plus 2. Cool. And what we need to know is they are saturated hydrocarbons. So saturated just means they have the maximum number of hydrogens. And you can see here, this is an example of an alkane. So this one, again, we think about our naming. We're going, there's 3 carbons down the longest end. So this is prop, and then the suffix for alkanes is ane. So propane is a 3-carbon chain alkane. And you can see I've also drawn it in its skeletal format here. So make sure you're comfortable with moving between the two. Now, something important to know about alkanes is that they only contain sigma bonds. So sigma bond means you have a head-on overlap between orbitals. Typically, it's going to be S to S, but it can also be S to P. So just be aware of that. But you don't need to stress too much about this part. It's just additional knowledge if you're really, really curious. Now, it will be a bit more important when we talk about alkenes in the next video. Now, shape is tetrahedral. So again, we're thinking back to module 2 with shapes of molecules. So tetrahedral shape for your alkanes. And you need to know how to draw this 3D model here that I'm going to box off. You need to know how to draw that. So apologies for me for getting away from that. But you need to be able to draw that. So whenever you're looking at that, you're thinking, I believe this dashed one means it's behind the page. This solid one means it's in front. And then the normal line just means it's in line with the page. So make sure that you are aware of that. And then again, just thinking back to module 2, with tetrahedral, bond angle was 109.5 degrees. There's 4 bonding pairs and known lone pairs. That is how you're going to justify the tetrahedral shape. So make sure that you are doing a review of module 2 for that. Now, melting and boiling points, again, very, very important. So in terms of the melting and boiling points, it comes down to properties. So if we increase the carbon chain length of an alkane, we have a longer chain, meaning we have more electrons. If we have more electrons, what does that mean? Well, it means that we have more London forces. And if there's more London forces, that means more energy is required to break said London forces. Hence, the melting or boiling point is going to increase. Branching is a bit more interesting, and we'll draw a diagram now. Are you happy? If we have this molecule here and another molecule of the same thing, they can just sit on top of each other. However, if we have this one with a branch here, you can see we've created a gap. It can't sit as comfortably on the other molecule there. So I hope that does make sense. It doesn't sit as nicely. So branching, if you have more branches, there's less points of contact. You can see here very nicely, apologies. You can see here very nicely, bam, 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 points of contact. However, here, there's few and far between. So less points of contact, fewer London forces, less energy is required to break said London forces, hence the melting boiling point decreases. Make sure that you are very, very comfortable with those explanations when it comes to exam. We also need to talk about the reactivity of alkanes. So alkanes have carbon to carbon sigma bonds and carbon to hydrogen sigma bonds, yeah? And the thing is about these bonds, right, is that they are very, very strong covalent bonds, and they are non-polar. So non-polar because the electronegativities of carbon and hydrogen are very similar. Now, this means that alkanes have a very, very low reactivity. So they don't really partake in many reactions, but we will talk about the ones that they do. So combustion is one of them. So combustion, we use alkanes as fuels, yeah? And it's very dependent on oxygen availability. So if we have complete combustion, then that means that we're fully reacting. So we're going to form carbon dioxide and water. I've just included state symbols for you there. Now, you do need to be able as well to balance these equations. So that's something that I'd ask you, I'd prompt you to do on your own time if you want to quickly pause the video. But essentially, always look, number of carbons, there's 2, so we're going to put a 2 here. Number of hydrogens, there's 6, so we're going to put a 3 here. So now we've balanced carbon and hydrogen, we just need to see what's left of the oxygen. So I've got 4 plus 3 is 7, so I'll call it 7 over 2. And you can do that. You can also try your left-hand side, right-hand side method, but I just sped through it there. Incomplete combustion as well can happen. So in incomplete combustion, we're forming carbon monoxide or soot. Yeah, carbon monoxide CO or soot C. And again, very similar thing. I've done those equations there. You can go back and check it if you want, but just make sure that you are comfortable with balancing those equations and knowing when we're having complete combustion or incomplete combustion. Now, the other big one with alkanes is they can form haloalkanes by a process called free radical substitution, which we're going to talk to in the next bit. Okay, and finally we get to talk about free radical substitution, which I will probably refer to as FRS for the rest of the video. Now, FRS, we are using homolytic fission to break covalent bonds using UV light. Now, UV light is a condition. Whenever you have your apparatus for FRS, you shine UV light on it, and that's going to help to break these bonds.
Now, homolytic fission we can define. It's the breaking of a covalent bond in which both atoms take an electron from the shared pair, forming radicals. Cool. Radical is a species with an unpaired electron, so an atom or group of atoms with an unpaired electron. That's a radical. Now, both atoms are getting an electron. In heterolytic fission, it's different. This is a different kind where one atom is going to take both electrons from the shared pair and you form ions. Now, how do I remember that? I just think homosexual, someone who likes the same gender. So, homo, both of them get the same. Yeah? So both of them will get one of those electrons. Whereas hetero, obviously heterosexual is different genders, meaning that heterolytic fission, one of them is going to get something different to the other one. That's how I try to remember it. Now, with FOS, it occurs in 3 steps, and these 3 steps need to follow you for the rest of this course. Yeah? Initiation is the first one. So in initiation, and I've just put the radical definition here for you, but in initiation, we have our halogen, and we shine UV light on it. Yeah? When we shine UV light on it, we're going to break the covalent bond, and that's going to form your radicals, the species with an unpaired electron. So you can see that all happening here. Yeah? Happy days. The next step is propagation, which gets a bit confusing. So if you're imagining FOS happening, I want you to think of it like a massive chamber, right? This chamber isn't near big enough to do it justice. But you have a massive chamber, and you've got a bunch of particles just flying around there, and you've shone UV light on it. So these reactions are just going off and off and off. So any radical can interact with any single normal molecule, right? And that's what happens. So the chlorine radical that you formed from the initiation step is going to interact with your alkane. Yeah. In this case, I'm using 2 carbons, ethane. Cool. So it interacts with ethane. And again, you won't be expected to draw the displayed formula for this with FOS, I don't believe. Normally it will be structural or it will be molecular. But I'm just doing this for diagrammatic purposes. But you can see here, that radical is going to attract the electron from the shared pair, meaning that the electron here is going to go onto the carbon. Right? So now you form an ethane radical and hydrochloric acid. Yeah? Again, you've got an ethane radical lying around. This reaction is just popping about in different spaces, so it can react with a chlorine molecule. Yeah? When it reacts with a chlorine molecule, you form chloroethane. Yeah? So you form chloroethane and you get a chlorine radical. So just make sure that you know this is what's happening in propagation, because those particles are just bouncing about, reacting with who knows what. Now, termination is the last bit where we have radicals that join together to form compounds. So for example, you form chloroethane, you can form butane, you can form chlorine gas. Make sure that you know that any radical that you form, which is literally should just be the one from the alkane and the one from the halogen, they can all form together in whatever combination, forming your termination steps. So part and parcel, that is free radical substitution. Just make sure you follow these steps, and they do commonly present in the same way. They will probably change the molecule, but the principle remains the same. So focus on that when it's in your exam. Okay, so now there are limitations with free radical substitutions. It's by far not a perfect process. Normally it doesn't produce a big yield of the product that you want, and it's also very, very difficult to control, because like we said, you just pop it in a container, shine the UV light, and hope for the best. Now, what are problems that can happen with free radical substitution? Multiple substitution is one. So what do I mean by that? We've got a halogen in excess. We've got a bunch of UV exposure. Reactions can occur multiple times. So just because we've done one round of free radical substitution, FOS, doesn't mean that we can't do it again. Remember, one of our termination products literally is the halogen. So why can't the bond undergo homolytic fission again? Yeah, no reason why it can't. So you can form mono, di, or tri, or even tetra alkanes. Yeah, we've shown different examples here where we have I've used butane. So we have examples where there's 1 chlorine, 2, 3. Yeah, a lot of stuff can happen. Another thing is going to be about isomers, structural isomers. So the halogen doesn't need to insert only under the chain. It can insert anywhere. So we have here 2 chlorobutane and 1 chlorobutane. No reason why it can't go into different places. Again, affects the properties, which we'll probably talk about more later when we get into organic chemistry. Yeah, just know that's important. Another thing is undesired products. Like we said, many termination products. Yeah, even in the first round of FOS, you can see here that we've got this one. I think that's hexane. 1, 2, 3, 4, 5, 6. Yeah, hexane. That can form because we have 2 propane radicals. Yeah, so just know you get undesired products. So those are your big 3: multiple substitutions, positional isomers, and undesired products. Those are going to be the main limitations of FRS. Okay, people, it's time to breathe. That is the kind of content side of this lesson done, but we need to test it with questions. So you've got 4 that actually. So one of them is about stating and explaining the trend and boiling point shown by some alkanes. Then you've got a multiple choice question about free radical substitution, then a 5 marker about free radical substitution, before finally just a bit of a explanation about homolytic fission. So pause the video, have a go, and we'll be in the answer. Okay, so getting into the answers now, we'll start with the first one. So this was explaining. So you saw that I was branching, right? We know what the trend is immediately. That's just something that you should try to memorize. That boiling point decreases with more branching. Cool. Now, again, it was this key term, and like I say, it comes up in the mark scheme. Surface contact, or the area of contact. Yeah, that's important. If you said that, then you can link it to the London forces or induced dipole, whatever you want to call it. And then if we're saying if there's less branching, right, or if there's less branching or if there's more, just always link it to what you said. But more branching means that we have less intermolecular forces. That's how I'd go with it. Dave just put the opposite here. So make sure that you're following those steps when you're answering that question. Now the multiple choice, I'll quickly just go back here. This was the issue, yeah? The first one, I'm completely happy. That is a propagation step, yeah? Number 2, these are the wrong products. So if a chlorine radical reacts with, that's pentane, yeah, you aren't going to form that. You're going to form a pentane radical, and you're going to form hydrochloric acid, yeah? Make sure you know that. And 3 is a termination step, meaning that your answer has to be D, only 1, yeah? Okay. Again, this is something that you just need to know. So read the question. Initiation, you're doing the homolytic fission with the halogen, and then radical reacts with the alkane, and then also that alkane radical you form reacts with the halogen, and you get your products. Cool. Termination, you link everything together. So again, putting that all together, you get your answers. Now, make sure you're not thrown up by the molecule they give you. This one wasn't too bad with cyclohexane, but it can get worse than that. So just know, again, you're following the same steps every single time. Don't let the molecule throw you off. And finally, you just had to explain why it was an example of homolytic fission. So we've got a covalent bond between Br and Br, and we're breaking it, and we're forming 2 radicals. And that is literally all you have to say, and then you're golden. Okay, I think that's been a lot of talking from me. So we're going to wrap it up with the A-star tips and send you on your way. So general formula of alkanes and spotting alkanes with your displayed formula, skeletal formula, is a very, very useful skill that you should have in A-level chemistry. Yeah, make sure that that's easy for you, because it will help you so much when you're doing questions. Yeah, just noticing that this is an alkane. There's not much I can do with this. Now, you need to use your concepts in module 2. So like we talked about a lot about shapes of molecule. We talked about melting and boiling point, which I guess is more module 3. But we've talked about things that came up earlier in the course. So make sure that you're still using that knowledge and applying it to organic chemistry, because it doesn't just fade away. Now, processes of free radical substitution, we talked about, it's always those same 3 steps: initiation, propagation, termination. Always follow that, and you should be fine. And then also just being comfortable with writing out the equations for free radical substitution. Again, useful skill. I'd practice it. Just make sure that you can just send it off like that. Again, don't let the molecule they give you throw you off in the exam. What not to do? Definitions. Really, really easy marks. I always emphasize about getting definition marks. So radical, homolytic fission, heterolytic fission, these are probably the main ones we covered in the lesson today. Make sure you can define all of those. Now, the reaction mechanism that I drew with the displayed formula for free radical substitution is good for showing you what's happening. However, in the exam, it's very unlikely that they'd ask you to do that. Reaction mechanisms we'll get to later, but not for FRS, so don't worry too much about it. Don't waste time. And something that's really, really important, a lot of people miss out, is that dot for radical. Please, 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 please don't forget the dot for radical, because they will look for it and mark you down if you forget it. So make sure that you're putting that in the question, because a lot of people do forget, and it is an easy mistake to make. So that's a wrap on the video today. I hope it was really, really helpful. If you did find it useful, please like and subscribe to the channel. We are getting very, very close to 1K, which would be absolutely amazing. So I can only encourage you to please, please subscribe. It means a lot to me. Any questions at all about anything I've said about organic chemistry or about alkanes, drop them in the comments below, and I'll do my best to answer. We've also got our TikTok and our Instagram, both at A Demola, dropping content on there weekly. And that's all for me. So thank you so much for listening. Hope it's been helpful, and I'll catch you in the next one. Bye for now.